Bismillahirrahmanirrahim and Assalamu alaikum. Welcome to the lecture 12 of Discrete Structures CSC 102. In the previous lecture we have studied floor and ceiling functions. We have studied also the definition of proof and some methods of proofs, in which we have studied direct method of proof. We have proved some theorems also. I have also explained you what is the method of disproving a statement or a theorem by a counter example. We have also studied a method of contradiction, which is the indirect method of proof. Today we will continue the indirect proof, in which we shall study the method of contrapositive and some other methods. But before that, we study what is the mod functions, what is the relation between divisibility and floor functions. We shall also study the mod congruence and the relationship between contrapositive and contradiction methods of proof. So let's start. What is mod functions? Mod function 13 mod 24. What does it mean? If we divide 113 by 24, here you can see the usual division is given. So 24 fours are 96 and we are left 17. So what is 17 here? 17 is the remainder. So 113 mod 24 is basically equal to 17. So there is a problem here. And what is 4 here? 4 is the quotient, and 113 div 24 is equal to 4. And here 113 mod 24 is equal to 17, or we can say this is congruent to 17. Similarly, if we consider minus 29 mod 7 and we divide minus 29 by 7, we can see that minus 5s are minus 35, and if we take if we change the sign here, we have the remainder is 6. So minus 29 mod 7 is basically the remainder, and the quotient here minus 5 is minus 29 div 7. So now if we revise the definition of div and mod, we have already seen these definitions. Given an integer n and a positive integer d, so here you can notice that n can be any integer. It can be positive, it can be negative, but the divisor d must be positive, it cannot be negative. Then n div d, this is basically the integer quotient obtained when n is divided by d, and n mod d is basically the non-negative integer remainder obtained when n is divided by d, as we have seen in the examples. And symbolically, if n and d are integers, d is greater than 0, d must be positive, then n div d is basically the quotient, n mod d is basically the remainder, where if and only if n is equal to dq plus r, which we have seen in the division algorithm, where q and r are integers and r must be greater than or equal to 0, but must be less than the divisor. So you can imagine why it is so, why r is less than d, as we in the previous examples, when 24 divides 113, 24 fours are 17. If we have here 24, then we can then the remainder, then we can multiply 24 5s are 1, whatever here is, and we get the remainder 0. So we cannot obtain the remainder equal to the divisor, just as we have studied in earlier classes. So now, what is the relation between divisibility and floor function? Here we have a theorem which shows the relationship between divisibility and floor. If n is any integer and d is a positive integer, and if q is what? Q is basically the quotient, and quotient can be written as n floor of n by d. We will see in the examples after this theorem that why we can write the q as a floor function of n by d, and r is equal to n minus d floor of n by d. Then we can write n is equal to dq plus r, where r must be greater than or equal to 0, but it must be less than d. Now we prove the theorem. Suppose n is an integer and d is a positive integer. Q can be written as the floor of n by d, and r is n minus d into n floor of n by d. Then we must show that n can be written as dq over dq plus r, and r satisfy this inequality. So if we take the left hand side here, this dq plus r, d can be written, so q can be written as floor of n by d, plus r can be written as n minus d into floor of n by d. If we simplify this, this will be cancelled out with this, and we are left only with n. So this is proof that dq plus r is equal to n. Now what is left to be proved? Now we have to prove r must be greater than or equal to 0 and less than t. As we know that q is the floor of n by d, thus by definition of the floor function, n by d must be greater than or equal to q and less than q plus 1. By the definition, here we have applied the definition of floor function as we have studied the definition of floor function, that floor of x is equal to n such that x is greater than or equal to n but less than or equal to n plus 1. So we have applied the same definition here on floor of n by d. Here we can write n by d greater than or equal to q less than q plus 1. We need to be proved r is greater than or equal to 0 and less than d here. So what we do in next step, we multiply q on both, d on both sides. Here we have d on in the denominator. We multiply d on both sides of inequality, you can say on all three sides. So we obtain dq is less than or equal to n less than dq plus d. So here we multiplying up all parts by d, and so now we can take dq here, and from here from both sides we can write n minus d, or you can say that we subtracted d on all sides of this inequality, just like this, dq minus dq less than or equal to n minus dq less than dq plus d minus dq. So here dq cancel, here dq cancel, and we have obtained 0 less than or equal to n minus dq less than d. Now as we have in the definition that q is n by floor of n by d, so here instead of q we can write floor of n by d, and we know that n minus d into floor of n by d is equal to r. So here we can write r is greater than or equal to 0 and less than d, so which was required, and we have proved that the n is equal to dq plus r, where r is greater than or equal to 0, less than d, where q is floor of n by d, and r is n minus d into floor of n by d. So now we see an example how we use the floor functions to calculate mod and div functions. Here we have used the floor notation to compute 3850 div 17 and 3850 mod 17. So as we have seen in the previous theorem that n div here, that q is basically the floor of n divided by d. So if we want to calculate the quotient, which is n div d, so we can write it as floor of n divided by d. So we divide 3850 by 17, we get 226.4705882 and so on. Now if we take the floor of this function, we get obviously 226 by using the definition of floor functions. So this is our q, the quotient. Now to calculate 3850 mod 17, we know that a mod d, this here, r is basically r is equal to n minus d into floor of n by d. So using this definition we can write here n, here it is n, and this is d. So n minus d into floor of n divided by d. So 3850 divided by 17, we have divided already this, calculated this is 226, so we write here 226. We multiply it by 17 and we subtracted the result, this number from this number, we get 8. So this is our r, the remainder. So this is how we can calculate the div and mod functions using the floor functions. So this is one type of mod function here, which gives us the remainder after the division of two numbers. Now there is another mod function which is basically the mod congruence. So what is the mod congruence? By definition, let a, b be any two integers. These two integers can be negative, can be positive, anything, and n be a positive integer. So the divisor must be a positive integer. We say that a is congruent to b modulo n. This is read as a is congruent to b modulo n, and it is written as a is congruent, this is basically the symbol of congruence, b mod n, or this is read as a is congruent to b modulo n if and only if n divides the difference of a and b, or n divides completely b minus a. If n divides b minus a, then there exists some integer by the definition of divisibility, an integer k, such that b minus a can be written as the divisor into the quotient. K here is the quotient. For example, if we have 3 is congruent to 3 mod 17, then what does it mean? It means that 17 divides 3 minus 3. So whether it is true or not, this is basically equal to 17 divides 0. So every number divides 0, this is basically 0, so this statement is true. The next is 3 is congruent to minus 3 mod 17. So we can see the solution on the next slide. 3 is congruent to minus 3 mod 17. So false. This is false because 3 minus 3, basically this is b minus a. So minus 3 minus 3 is basically minus 6 here, and minus 6 is not divisible by 17. So 3 is not congruent to minus 3 mod 17, and we can write it as 3 is. Now the second example is 3 is congruent to minus 3 mod 17. We can see here on the next slide, minus 3 is congruent to 3 is congruent to minus 3 mod 17. This statement is false because minus 3 is basically minus 6, and 17 doesn't divide minus 6. So this implies that 3 is not congruent to minus 3 mod 17. So next example is 172 is congruent to 177 mod 5. So if we see here, 177 minus 172 is basically 5, which is a multiple of 5. So 5 divides 177 minus 172. So this implies 172 is congruent to 177 mod 5. This is true. The next statement is, the next example is minus 13 is congruent to 13 mod 26. So here we can see that 26 divides 13 minus, here 13 minus 13 is basically 26, which is divisible by 6. So this the fourth example where the minus 13 is congruent to 13 mod 26 is true. So in the mod congruence we see whether that the n divides b minus a or not. If it divides, then we say that this congruence is true. If not, then we say that this congruence is false. Next are some congruence identities. Let n is greater than 1 be a fixed and a, b, c, d be any arbitrary integers. Then the following properties hold. The first property is basically reflexive property. In reflexive property, what we have, a is congruent to a mod n. What does it mean? That every number is congruent to itself always. For example, if we say 3 is congruent to 3 mod n can be anything here, n can be 6, 8, 9, 10, 2, 3, anything. So if we write here, so for example 7, so 7 divides always 3 minus 3. So 3 minus 3 is basically 0. This means that 7 divides 0, so every number divides 0. So this is true. It means that every number is congruent to itself always, no matter what is the n. So this is the reflexive property of congruence, mod congruence we can say. The next is symmetric property. In symmetric property, symmetric property says that if a is congruent to b mod n, then b is congruent to a mod n. That means that if we have 2 is congruent to 4, if we say that 2 is congruent to 4 mod 2, or you can say that then 4 is always congruent to 2 mod 2. Here n is 2, A is 2, B is 4. So in this case 2 divides 4 minus 2. This is 2. 4 minus 2 is 2, so 2 divides 2. In this case 2 divides 2 minus 4. Here 2 minus 4 is minus 2. So 2 divides also minus 2, which gives us minus 1. 2 is equal to, so we can say here that the congruence, mod congruence, is always symmetric. Symmetric means if A is congruent to B mod n, then B is always congruent to A mod n. The next property is transitive property. This says that if A is congruent to B mod n and B is congruent to some other number C under the same modulo n, then we can say that A is congruent to C modulo n. This, for example, 2 is congruent to, as we have written here, 2 is congruent to 4 mod 2, and 4 is congruent to 8 mod 2. This implies 2 is congruent to 8 mod 2, and this we can easily verify that. Here we have 2 divides 4 minus 2, which is 2, so it is true. Here 2 divides 8 minus 4, so which is also true because 2 divides 4. Then here in this third case we have 2 divides 8 minus 2, which is 6. So 2 divides 6, so this is also true. So this is basically the transitive property of mod congruence, and this is also always true. The next property, D, is basically if A is congruent to B mod n and C is congruent to D mod n. Though if we have two congruence under the same modulo n, then we can say that A plus C is congruent to B plus D mod n under the same modulo n, and also we have A into C is congruent to B into D mod n. So this is also a property of mod congruence. The next property, for the property D, we can choose example as I have shown you the examples for the mod transitive property and symmetric property. You choose any two mod congruence, and you can verify that this congruence and this congruence is always true under the same modulo n. The next property E is if we have A is congruent to B mod n, then A plus C is always congruent to B plus C mod n, and A dot C is congruent to B dot C mod n. That is, we can add up any number, any fixed number on the both sides of A and B. Here we can add up or multiply the same number to A and B, then the congruence will remain. The congruence of A and B, here if we have A is congruent to B mod n, then we can add a same number on both sides. Even then this congruence will remain true. The next property F is basically if A is congruent to B mod n, then we can take the powers, any finite power of A and B, then the congruence remains true. For example, for any positive integer k is any positive integer. For example, as we have seen, as we have congruence here, 2 is congruent to 4 mod 2, then we can take the power 3 here and power 3 here. Then it remains, this congruence remains true because 2 power 3 is basically 8 and is congruent to 4 power 3 is 1664 mod 2. So here 2 divides 64 minus 8, and this is basically true, because 2 divides 56. So this is another property of mod congruence. So we have seen some properties of mod congruence. We can prove these properties by using some direct or indirect methods. We will also study these congruence relations and congruence identities in detail when we shall study the relations in the next lectures. So for the mod congruence it is sufficient. Now we see a theorem related to the mod congruence. This theorem we shall prove by direct method. If k is any integer such that k is congruent to 1 mod 3, then k cube is congruent to 1 mod 9. This is what we have to prove, and we will use method of direct proof to prove this theorem. So as we know that in the direct method of proof, we suppose that first of all we write the statement in the universe which we have written here. For all k belongs to z, which means for all integers, if k is congruent to 1 mod 3 implies then k cube is congruent to 1 mod 9. So now we suppose that the statement here, which is after if, the conditional statement, the hypothesis of the conditional statement, we suppose it is true, and we have to prove by using some already existing mathematical results that the conclusion here of this conditional statement is true. So we suppose that k is congruent to 1 mod 3. What does it mean? By the definition of mod congruence, we can say that there exists some integer n such that k minus 1 is equal to 3n. By the definition of mod congruence, then 3 divides 1 minus k or k minus 1, as we know that the mod congruence is symmetric. If 3 divides k minus 1, then k minus 1 can be written as 3 into n. So there exists some integer n. So this is what we have written here. We take the 1 on the, this implies k is equal to 3n plus 1. So k can be written as 3n plus 1. We take the cube on both sides here. K cube is equal to 3n plus 1 whole cube. We open up the cube, as you know that a plus b whole cube is equal to a cube plus b cube plus 3ab square plus 3a square b. So this is what the formula which we have studied in your 9th or 10th class. So the next we take this plus 1 onto the other side. Here we can write k cube minus 1. We are left with this, and we can take common 9. 9 3s are 27, 9 3s are 27, and 9 1s are 9. So this number into 9. Now the expression here written, this is k cube minus 1 is equal to this. This is basically some integer. Basically, as we have we said that n is some integer, so n into 3 is an integer, n cube is integer, n square is integer, n square into 3 is integer, and if we take the sum of 3 integers it will remain integers. So we say that this integer is m. This may be any integer. So k cube minus 1 can be written as m into 9. So what does it mean? So by definition of this, what is the definition of this? It means that 9 divides k cube minus 1. If 9 divides k cube minus 1, then k cube minus 1 can be written as 9 into some integer, we say that m. So this is what we have obtained here. K cube minus 1 can be written as m into 9. So what does it mean? It means that k cube is congruent to 1 mod 9, which is the conclusion of this conditional statement given here. So this is what we have to prove. So this theorem has been proved that if k is an integer such that k is congruent to 1 mod 3, then k cube is congruent to 1 mod 9. Next we discuss another method of which is an indirect method of proofs, method of proof by contrapositive. So you know that what is the contrapositive of a conditional statement. If we have a conditional statement P implies Q, then the contrapositive of this statement is not Q implies not P. So this is what the contrapositive we have studied in logic, the contrapositive of conditional statement. Here we shall take the contrapositive of given universal conditional statement as the first step in this method of proof is that they express the statement to be proved in the universal conditional statement as we do in the direct methods. Then rewrite this statement in the contrapositive form as we have studied the contrapositive in logic. We have written the universal conditional statement into the contrapositive form, that is, for all x and d, if q of x is false, then p of x is false. This is what we have written here. Q of x is false or not q is true implies not p is true. This is the same. Then after rewriting this statement into contrapositive form, then we prove this contrapositive statement by direct method of proof. By direct method of proof, what we shall prove that if q of x is false, we suppose the hypothesis of this conditional statement is true, and then we shall prove that p of x is also false. As you can see that we shall suppose here that x is a particular but arbitrarily chosen element of D such that q of x is false, or we shall prove that not q of x is true. Then we by following the sequence of steps, we shall prove that p of x is false, or we shall prove that not p of x is true. These two are the same things. So this is this is called the method of proof by contraposition or contrapositive method. We take an example, a proposition, and we prove this proposition by the method of contraposition. So what is the proposition? For all integers n, this is basically the domain, if n square is even, then n is even. So this is what we have to prove. So first of all, this statement is basically written as the universal conditional statement. If n square, for all integers n, if n square is even, then n is even. So we first of all we write the contrapositive of the given statement. For all integers n, if n is not even, then n square is not even. This is the contrapositive of given statement. Now we shall prove this contrapositive statement by the method of direct proof. We suppose the hypothesis here is true, that is, n is not even. If n is not even, then obviously n will be odd. So we have to prove that n square is not even, that is, we have to prove that n square is also odd. If n square is not even, then obviously n square will be odd. So first of all, we suppose that n is odd, That is, then n can be written as 2k plus 1, as the usual odd numbers can be written for some integer k. And we have to prove n square is odd, so we take the square on both sides. N square is equal to 2k plus 1 whole square. We open up the square, which is a plus b whole square, which is a square plus b square plus 2ab. So this we have obtained 4k square plus 4k plus 1. From these two first terms we take 2 as a common, and we can write 2k square plus 2k into 2 into 2k square plus 2k plus 1. Now, as in the definition of odd number, we have supposed that k is any integer. So k square is integer. If we multiply k square by 2, it will remain integer. 2 into k is integer. Sum of two integer is also an integer. We know that. And we have written the n square as 2 into some, here some integer, an integer, it could be m plus 1, where m is 2k square plus 2k, where m is 2k square plus 2k. So n square, now we have succeeded to write n square as 2 into some integer plus 1, which is the definition of odd number. So thus, by definition of odd number, n square is odd, this is what we have to prove, that n square is not even, that is, n square is odd. So the theorem, the given statement has been proved, that for all integers n, if n square is even, then n is even, as we have studied in logic that the conditional statement and its contrapositive are logically equivalent. We have proved it by using truth tables also. Now, if we are succeeded to prove the contrapositive of a statement is true, then its original form, the original conditional form, will also be true. So this is another method of proving a conditional statement. But this method has a disadvantage, that this method can only be applied on the statements which can be written as the universal conditional statements. Then we write its contrapositive. If the given statements are not in the form of universal conditional statements, then we cannot apply this method, because we cannot write their contrapositives. The next is the relationship between contrapositive and contradiction proofs. The contradiction proofs we have already proved some theorems, and in the next slides I shall give you some other proofs of the statements by using contradiction methods, and at the end we shall prove two very famous and classical theorems by using contradiction method. Now, what is the relationship between the contrapositive and contradiction method of proofs? In a proof by contraposition, the statement, the universal conditional statement for all x in D, if p of x then q of x, we write this statement into an equivalent form, which is the contrapositive form of the given statement, and then we prove this statement by using the method of using the direct method of proofs. And what is this? We suppose that not q of x is true, and then we prove not p of x is also true. Symbolically, or in the form of figure, we can illustrate this as, we suppose for an arbitrary x which is an element of D, we suppose that not q of x is true, and after the sequence of steps, we prove that not p of x is also true. What we prove in this contrapositive method, that not p of x is true. Whereas in the method of contradiction, what we do, in the method of contradiction, we suppose that the p of x, the hypothesis in the conditional statement, is true, and we try to prove that not q of x is true, or we try to prove that q of x is false. But not p of x is a basically in what we do in the method of contradiction. If this process is illustrated in figure, then we can write, we suppose there exists x in the domain D such that p of x is true, and we suppose that basically in the method of contradiction we suppose that p of x is true, and this is basically the hypothesis. And what we have to prove, that q of x, we suppose that q of x is false in the method of contradiction. But after the sequence of steps, we arrive at some contradiction, that what we have supposed, that not q of x is true. After some sequence of steps, we arrive at some contradiction that not p of x is true. And at this stage we say that what we have supposed was a contradiction, and because we arrive at the contradiction p of x and not p of x. P of x by the hypothesis, this is true, and we arrive at, after some sequence of steps, that not p of x is true. So at the end we always try to obtain some contradiction, that not p of x is true. This in fact, the method of contrapositive, in method of contrapositive we also prove not p of x is true, and in the method of contradiction we arrive at also not p of x is true. In both methods we do the same steps, but the method of proving the two statements are basically, the method of proving the two statement is basically the same, but we arrive at the same conclusion in both methods. Again, if we try to prove the same statement, same proposition which we have proved by using the method of contrapositive, now we prove the statement by using the method of contradiction, then you will get an idea what is the relationship between these two methods. So for all integers n, if n square is even, then n is even. This is the same statement. We now are going to prove the statement by using of method of contradiction. So we suppose that, again, what we have to prove, n is even, we suppose that this is false, or not q of x is true. We suppose that n is not even. If n is not even, then n will be odd. If n is odd, then we can write n as 2k plus 1 for some integer k. If we take the square on both sides, n square is equal to 2k plus 1 whole square. This is equal to 4k square plus 4k plus 2 plus 1. Again we write this as 4k square plus 4k. We take common 2 into 2k square plus 2k plus 1. So n square is again written as 2 into some integer plus 1. What does it mean? It means that n square is odd. But here in the supposition we have suppose that the hypothesis of this conditional statement is true, but we arrived at what? N square is odd, but this was the hypothesis, and hypothesis was true. Here at the conclusion, at the end of the proof, after sequence of steps, we have arrived at that this p of x, if we suppose that p of x is this and this is q of x, we suppose that p of x is true, and we have arrived at that not p of x is true. So in method of contraposition, we also try to arrive at not p of x. In the method of contradiction also, we automatically arrive at not p of x. And in the method of contradiction, we say that here p of x, by the hypothesis we have supposed that it is true, we have arrived at not p of x is true. Now there is a contradiction that p of x is also true, and by the sequence of steps we have proved that not p of x is also true. So this is contradiction in our logic, that we are saying that p of x is true in the start, and at the end we have arrived at that not p of x is true. So this is a contradiction, and we say that what we have supposed, suppose n is not even integer, this supposition was wrong, and then what will be true? The given statement will be true. This is what the method of contradiction says. So in both methods the procedure is same, but the method is different. Now I hope that you understand that the relationship between contradiction and contrapositive methods of proof. Now we have studied a method of in method of proofs, the direct methods, the indirect methods. In indirect methods we have studied a method of contradiction, method of contrapositive, and we have also seen some method by disproving a statement by giving some counterexample. Now, which method we use, or what is the preference of methods to be used to prove some given statement? So if we are not given some obvious clues or obvious conditions, first we try to prove any given statement by using method of direct proof. Then we look, if we do not succeed in proving any statement by using direct method, then we search for a counterexample to disprove the given statement. So this is basically the order of preference in using the methods to prove a given statement. If you are not succeeded in finding some counterexample also, then try method of contradiction, and then at the end try the method of contrapositive. So this is not the hard and fast rule. This is not the must that you must follow these steps to prove a given statement, but usually and this pattern should be used in proving some given statement which we have to prove. So next is at the end of the method of proofs, I give you two classical theorems which are very famous statements to be proved in discrete mathematics. Square root of 2 is an irrational number. We have to prove this. So now we use the method of contradiction. If you try some direct method to prove this statement, you will not be succeeded by using direct method to prove this statement. Then if we look up a counterexample, then we are unable to find some counterexample. Therefore we try to use the method of contradiction, and we are succeeded to prove this statement by using method of contradiction. We, as usual, by the method of contradiction, we suppose that square root of 2 is not an irrational number. If a number is not irrational, then it must be rational. We already know this. So we suppose that under root 2 is rational. If under root 2 is rational, then we can write under root 2 as the quotient of two integers m and n, as we have written here. Here we have supposed another condition. We have imposed another condition on m and n, that then there are integers m and n with no common factors. With no common factors means that m and n must be relatively prime, means GCD of m and n must be 1. GCD of m and n must be 1, or you can say that there is no common factor in m and n. So we write under root 2 or square root 2 is equal to m by n, which is the form of usual rational number. Now we take square on both sides. We obtain 2 is equal to m square by n square, or equivalently we multiply n square here. We can write m square is equal to 2n square. Now m square is written as we have supposed here that n is any integer. If n is integer, then n square is also integer. If n square is integer, then m square can be written as 2 into some integer. What does it mean? It means that m square is even. If m square is even, then m is also even, as we have proved the previous theorem. If n square is even, then n is even. We have proved in the previous example here that for all integers n, if n square is even, then n is even. So we have proved it. So in this here, if m square is even, m square is even because m square is written as multiple of 2 into some integer, then m square is even. By the previous theorem, then m is also even. If m is even, then m can be written as 2 into some integer k, and if we take up square, m square is equal to 2k whole square, which is 4k square. The 4k square, this can be written as 2 into 2k square, this, and we have this is equal to, basically here, as we have seen that m square is equal to 2n square. Here we have m square is equal to 2n square. If we write m is equal to 2k, put the value of 2k here. If we put the value of 2k here, we obtain 4k square is equal to 2n square, and 2 is cancelled out with 2 here, so n square is equal to 2k square. We can write it. Now n square is equal to 2 into some integer. What does it mean? It means that n square is even. If n square is even, then n must be even by the previous theorem. So n is also even. If n is even, then n can be written as 2 into some integer k, you can say that s. Now m is also, we have written 2 into k. Now here we have that we have suppose that GCD of m and n is equal to 1, or m and n have no common factors. Here we have arrived that 2 is the common factor between m and n, because m by n is equal to 2k over 2s. So 2 is basically here the common factor between m and n, which is basically the contradiction to our supposition that m and n have no common factors. So supposition was wrong, then what will be true? Under root 2 square root 2 is an irrational number will be true. So similarly we can prove the second theorem, in which we have to prove that 1 plus 3 into square root 2 is irrational. We take the same steps we have taken in the previous theorem. We suppose that 1 plus 3 into square root 2 is rational. We write it as this. We take the 1 on the other side, we take the LCM. Now this is basically the rational, where we divide 3 on this side, because a is integer, b is integer, a minus b will also be integer, b is integer, 3 into b is integer, and we have integer over integer, which is square root 2. It means that square root 2 is rational, which is a contradiction. Therefore, because we have already proved that square root 2 is irrational number, so here we also conclude that this number is an irrational number. So for today it is sufficient, I think, and we have finished the topic method of proofs and number theory. In the next today's what is the lecture summary of today's lecture. Today we have studied mod function, divisibility, floor, mod congruence, indirect proof, method of proof by contrapositive. We have seen also the relationship between contrapositive and contradiction methods of proof. So the method of proofs and number theory we have finished today. In the next lecture we shall start the set theory, and up till then Allah Hafiz.